In this example, we're asked to determine if a certain collection of vectors is a subspace of R2, which would be the set of all two-dimensional vectors with real entries. So here we've got a subset. We've got just the vectors whose entries are both greater than or equal to 0. If you're picturing this in the xy plane, the x and y coordinates are both greater than or equal to 0, so we're either on the positive x-axis, on the positive y-axis, if one of those entries is 0, or else we're in quadrant 1. So that's a way if you like to visualize these things. Now, theorem 4.1.1 says that if we have a subset of vectors within a vector space, we really only need to check 3 conditions. We don't have to go through the whole list of conditions for a set to be a vector space. So we have to check number 1, does it contain the 0 vector? And so in this case, the 0 vector in R2 is this vector here, 0, 0. Both of these entries are greater than or equal to 0. So yes, the 0 vector is contained in this set. The second condition we have to check is if we take any 2 vectors in this subset W, is the sum of those vectors also in W? So to prove something like that, you have to be careful. You can't just choose 2 specific vectors that are in W and show that, okay, their sum is also in W, so that shows that this will always work. That's not valid. What we have to do is take 2 generic vectors in W. So I'll call this x1, y1, and we can let v2 equal x2, y2. Oops, okay, there we go. Where x1, y1, x2, oops, y1, x2, y2 are all greater than or equal to 0. Because we want both of those vectors, v1 and v2, to belong to W. So the entries all need to be greater than or equal to 0 because of this condition here. Now we look at the sum of those vectors. So I'm going to scooch this up a little bit and take the sum, v1 plus v2. So to add 2 vectors, you just add the corresponding entries. So the first entry will end up being x1 plus x2. The second entry is y1 plus y2. And the question is, does this vector belong in W? So, and the answer is yes. I mean, if we take a number that's greater than or equal to 0, add another number that's greater than or equal to 0, and that sum would definitely be greater than or equal to 0. Same in the y component here. So yes, condition 2, the subset here is closed under addition. So the third condition that we have to check is it closed under scalar multiplication? And this is where we're going to run into problems. You might have suspected this from the beginning. Okay, I'm going to slide down here. So the third condition is it closed under scalar multiplication. I just like to have it in writing, but I'll abbreviate here. To satisfy that, we need to take a generic vector in W. So I could use that same v1 that we had in the previous problem. And C needs to be any scalar, any real value. And the question is C times v1 in W? So if we want to show that yes, C times v1 would always be in W, then we have to take just a generic vector C. But to show that this condition fails, we can take a specific scalar, I'll use -1, and a specific vector v, I'll use 1, 1. So this is certainly in W. Both entries are greater than or equal to 0. This is a scalar, but this, when we multiply C times v1, we get the vector -1, -1. And this does not belong to W. So the answer here, is it closed under scalar multiplication, is no. And since we cannot say that all three conditions are met, since this condition fails, this is not a subspace of R2. The answer here is no, because the closure under scalar multiplication fails.